Okay, recording has started.
Okay. So, hello everyone, and welcome to this edition of the Gauge Gravity by the Gauss seminar. We are very happy to have with us today Professor Frithjof Karsch from Bielefeld University. Frithjof got his PhD from Bielefeld University, after which he did postdocs in CERN and UIUC. He works in the area of lattice QCD, specifically lattice QCD at finite temperature and finite density. Today, he's here to tell us about the chiral phase transition in the chiral limit of QCD. And yeah, we're all very interested to hear about it. So over to you, Frithjof.
Okay, so I shared my screen. I hope you see it.
Yes.
Okay. Yeah, so as Prasad said, what I want to talk about is some new results on the chiral phase transition in QCD. So I will start with a quite general introduction to the QCD phase diagram, and then I will discuss a bit how one gets from the pseudo-critical temperature of QCD, which one has at physical values of the quark masses, to the chiral limit, and how one can use this sort of unphysical situation of the chiral limit to generate some interesting constraints on the location of the so-called critical endpoint, which is searched for also experimentally in heavy ion collisions. So let me start with some general remarks about how we think about the phase diagram of QCD. So we think of the phase diagram of QCD as essentially the plane of temperature and baryon chemical potentials. I later on will also introduce strangeness chemical potentials, but so sort of we think of this plane, and in the early 80s it has been understood that there should be a phase transition going from the ordinary QCD vacuum and low temperature physics of strong interactions where hadrons exist as basic degrees of freedom. From that one might go to a region of high temperature and high densities where QCD shows up in its platonic degrees of freedom. Perturbation theory might be valid, and one talks about this region as the quark-gluon plasma. So the early thinking was that there is a phase transition between the low temperature regime and the high temperature regime, maybe a first order phase transition or a second order phase transition. Today we think it is not really a phase transition at vanishing baryon chemical potentials, but a rapid crossover. However, when one goes to large baryon chemical potentials, there is still the possibility that one finds a region of first order phase transitions in the phase diagram of QCD, and the separation point between this possible first order region and the crossover kind of transition at low temperature, at low baryon chemical potentials, that is called the critical endpoint. And there is a huge experimental program going on at various accelerators to look for this critical endpoint and also the properties of the transition from low to high temperature. So there's the LHC experiment, which basically probes a small chemical potential region. Then there's the RIG experiment, which is able to change beam energies and in this way probe a wide range of finite baryon densities. And there are also plans for future accelerators which are quite advanced. So in near future we will see also experiments from the so-called FAIR experiment in Germany at GSI. So one of the basic questions one has in studies of the QCD phase diagram is finding this critical endpoint in the QCD phase diagram and putting constraints on its location. And I will come back to that later on again. So in theory, to study properties of QCD at finite temperature and finite density, what is done is to regularize the basic theory, quantum chromodynamics, on a four-dimensional space-time lattice. And the first simulations of such a theory have been performed by Mike Kreutz, end of the 70s in the last century. So I think from this basic setup, what I will need in the following only is that the partition function of QCD is written as a path integral over fermion fields and gauge fields. The fermion fields are integrated out to generate this famous fermion determinant. And the fields are discretized on a four-dimensional space-time lattice. The fact that the partition function is a trace over, in general, exponential of the Hamiltonian forces the path integral to be bounded or let's say the action to be bounded as an integral over Euclidean time in the temporal direction, and this bound in the temporal direction is used to introduce the temperature in the theory. So usually what one does is one performs simulation on space-time lattices with a certain extent in the time direction, and this time direction constrains the temperature of the system, and that number of time points in the time direction and the fact that one wants to have a finite temperature also introduces a non-vanishing lattice spacing. So eventually one wants to trust lattice QCD calculations, one wants to let the lattice spacing go to zero at fixed temperature, which means one wants to go to infinitely large lattices. So that is one of the big problems in lattice QCD calculations. The other one is that the introduction of fermion chemical potentials makes the measure of the path integral complex, and one generally has no good numerical techniques to deal with this complex determinants. So usually what I will discuss in the following is the use of expansions around vanishing chemical potentials where the fermion determinant is real and positive, and one then gets results in terms of a Taylor series in the chemical potentials. So let me start with the discussion of the QCD phase diagram, not as function of temperature, but as function of the quark masses. In a theoretical calculation, of course, we can vary the quark masses, and the variation of the quark masses allows to discuss the QCD phase diagram in the quark mass plane. And that early on has been done by Pisarski and Wilczek, exactly more or less 40 years ago. And they came up with this left-hand phase diagram in the quark mass plane, saying that the phase transition in the quark mass plane becomes, in the chiral limit, a second-order phase transition when one changes the quark masses from its physical value and lets the light quark masses go to zero, whereas one keeps the strange quark mass more or less fixed. However, as they discuss, when one changes all three quark masses, up, down, and strange, and moves them towards the chiral limit, then it is expected from their model calculations that there should be a first order phase transition appearing in the chiral limit. This kind of a phase diagram has been discussed a lot. The Frankfurt group around Ove Philipsen generalized this kind of a phase diagram to the right-hand phase diagram and said that there's such a point in the strange quark mass direction exists where the first order region is separated from a second order region is not quite clear. This endpoint strange tri-critical mass might as well be at infinite strange quark mass, and then one would end up with the right-hand phase diagram. So this is also a possible scenario for QCD and has been studied a lot, but the surprising outcome of the studies in the last years, in which many groups have been involved, also the group around Prasad and his PhD student Sipas Sharma, came to the conclusion that in fact this yellow region in the phase diagram does not seem to exist at all. So certainly there is no first order region at physical values of the strange quark mass, so the Pisarski scenario seems to be valid in that case. However, there also does not seem to be a first order region in the degenerate case of three light quark flavors, and this region, if it exists, shrinks if it exists at all, it shrinks to very, very small values. So it seems that also the three flavor gauge QCD theory has only a second order phase transition rather than a first order transition, which is quite surprising. Anyhow, this is the scenario we know at present in the quark mass plane. What I want to discuss today is this sort of three-dimensional version of the QCD phase diagram, where one has the temperature axis, a chemical potential axis, and also the possibility of varying the light up and down quark masses. In all this discussion, I will keep the strange quark mass fixed to its physical value. And as I discussed on the previous slide, what one expects at physical values of the light and strange quark masses at vanishing chemical potential, that is the upper corner of this three-dimensional phase diagram, one expects here to find only a rapid crossover transition at physical quark masses. And when one moves down to a vanishing light quark masses, still at vanishing chemical potential, then one expects to hit a second order phase transition in the chiral limit. And this second order phase transition might persist also at non-vanishing values of the light quark masses, and various model calculations suggest that there exists at vanishing light quark masses, so in the chiral limit, a tri-critical point where the second order phase transition turns into a first order transition. And this tri-critical point, as has been shown, actually provides an upper bound for the critical temperature at which, at physical quark masses, one might find a critical endpoint in the QCD phase diagram. So this critical endpoint, which I discussed in my first slide, which might exist in the situation of physical light and strange quark masses, and which one might search for in experiments, that its location is constrained by properties of QCD in the chiral limit. And what I want to discuss in my talk a little bit is how we get information on the chiral phase transition temperature, its dependence with the chemical potential, and how we can use that to put a bound on the possible location of a critical endpoint at physical values of the quark masses, which at present is not found and it's even not known whether it exists. So I want to discuss calculations of the pseudocritical temperature at physical masses, its extrapolation to the chiral limit, and then its extension to non-vanishing values of the baryon chemical potentials, which might allow to constrain the location of a tri-critical point and the critical endpoint. The method one uses in lattice QCD calculations is sort of borrowed from well-known studies in statistical physics, where one knows how to study phase transitions and properties of the phase transitions or properties of the theories in the vicinity of a phase transition. I put here a picture of the well-known Ising model and its discussion in terms of block spin transformations that have been introduced by Kadanoff, and its rescaling that has been introduced by Wilson in the 70s, in the last century, which led to the conclusion that the physical properties in the vicinity of a phase transition can be described by so-called generalized homogeneous functions, which describes the rescaling of the physical variables, so in general temperature, external fields or quark masses, under rescaling of a system, of the length scales in a system. So this rescaling of, let's say, the temperature-like variable by a scale factor is given by this property that a certain exponent, critical exponent appears, which defines the rescaling of free energies under scale transformations. So that is the basic concept of the randomization group introduced by Wilson. It allows us to say that the logarithm of the partition function, which is essentially the free energy of a thermodynamic system, is described by a certain singular part, which is just the generalized homogeneous function, which I introduced before. And then one can expand about this singular part in the vicinity of a phase transition and gets some additional regular terms in the description of the free energy of a thermodynamic system. So we know that under rescaling we have this free parameter B in the free energy, and this free parameter B can be used to eliminate one of the unknown variables or scale variables in the singular part of thermodynamic functions. So usually what one does is one expands these scaling functions ut and uh around the critical point, which is at ut, u3 being 0. And there's one variable which one calls ut, which doesn't break the basic property, the basic symmetries of the statistical system one is interested in, or in our case QCD, And there is another parameter called UH, which breaks the symmetries when one has a non-vanishing value of UH. So that is usually in spin models an external field parameter. In QCD, this is actually the quark masses. And one can use this rescaling of the generalized homogeneous function in such a way that one sets the variable related to the symmetry breaking parameter to a constant, let's say 1, and then the temperature and external field dependence appears in the first scaling variable. Then there are other scaling variables which we have no good control about, so-called corrections to scaling, and I will ignore them in the following of my talk. So what we know about the QCD partition function close to a phase transition point is that it is described by this singular part of the randomization group transformation functions, which is controlled by a temperature-like variable and an external field variable. The external field variable H we can relate to essentially the light quark masses, and to get a dimensionless quantity one usually introduces light quark mass divided by strange quark mass as a control parameter for breaking of chiral symmetry in QCD. And then there's a larger set of variables in QCD or other theories which do not break explicitly the symmetries of the theory. And this is, for instance, the temperature, but it is also the entire set of baryon chemical potentials which we might be interested in studies of the QCD phase diagram. And these parameters can be used to expand the various scaling fields in the vicinity of a critical point. So at the critical point, the scaling field T should vanish. That means the temperature should vanish and also the various chemical potentials should vanish. Okay, so this basic property one uses to study various thermodynamic observables. And the kind of observables you know from statistical models. One, of course, is first of all interested in an order parameter for the phase transition, which is the first derivative of the logarithm of the partition function with respect to the external field H. But then one is interested also in response functions, which are second derivatives, either with respect to the external field or with respect to the temperature, or also these kind of mixed derivatives or mixed susceptibilities which one gets by taking derivatives with respect to the symmetry breaking parameter and the temperature-like variables. And these susceptibilities in the vicinity of a phase transition usually diverge. They diverge with a certain power of a critical exponent. So there's this exponent delta, which plays a large role in studies of the phase transition, the critical exponent beta, which controls the behavior of the order parameter, and then the exponent alpha, which controls the behavior of a specific heat. In the QCD case, where the chiral phase transition belongs to the symmetry group of O4 spin models, the exponent alpha plays a sort of special role because it turns out to be negative. So specific heats in QCD do not diverge, which makes such an observable not so interesting for detecting phase transitions. So it's rather easier to find a phase transition by having these purely magnetic susceptibilities or mixed susceptibilities, which will diverge as a phase transition point. So the observables we use in QCD to study the chiral phase transition is, as I said, the order parameter. The order parameter is the first derivative of the logarithm of the partition function with respect to the symmetry breaking field, which are the quark masses. So usually one says that psi bar psi is the order parameter for chiral symmetry restoration. In order to make that a useful order parameter, one has to take care, as usual in field theories, handling divergencies. So one knows that the chiral condensate has an ultraviolet divergence and also an anomalous dimension. So one has to get rid of this additive and multiplicative divergencies by renormalizing the chiral condensate in a certain way. So usually what one does is one subtracts from the light quark condensate a fraction of the strange quark condensate, and one multiplies with additional powers of the strange quark mass to get rid of anomalous dimensions. And so having this order parameter, one can define susceptibilities, as I said, either by taking derivatives with respect to quark masses, or this mixed susceptibility, which is a temperature derivative of the order parameter. Or I can also discuss a mixed susceptibility by taking derivatives of the order parameter with respect to chemical potentials, because, as I said, the chemical potentials act like a temperature-like field in the scaling variables. When one gets close to a critical point, then we know thermodynamic quantities are described or governed by the singular part of the free energy. So we know that the order parameter is controlled by a so-called scaling function, which is given in terms of this particular combination of temperature-like and magnetization-like scaling fields, and power of the symmetry breaking field to the power of the critical exponent, 1 over delta. Similarly, one can describe the chiral susceptibilities by scaling functions f chi, or the mixed susceptibilities by the temperature derivative of this scaling function fg's, which are actually all well understood and related to a certain scaling function ff, which is the singular part of the free energy that I introduced before. So the scaling functions are well known for various symmetry groups, and for the QCD case, in the vicinity of a critical endpoint, what is relevant is the Z2 symmetry group. When one discusses the chiral limit, the relevant symmetry group is actually the O4 group, as I said before. And one knows a lot of things about these scaling functions. What is important for the determination of a critical temperature is that the susceptibility, that the scaling functions that control the divergence of the susceptibilities, f chi and fg prime, they have certain maxima, and one uses this maximum of the scaling function to define pseudo-critical temperatures at non-vanishing external fields. So what is relevant in the following is that the scaling functions fg prime, f chi, and other scaling functions, they have peaks at different values of the scaling field Z. And these different peaks also means that the value of a pseudocritical temperature, which you can extract by looking at peaks of the chiral susceptibility or the mixed susceptibility, are not unique function in its own. They only become unique in the chiral limit. So this is what I want to discuss next. I want to discuss the determination of various pseudocritical temperatures at physical values of the quark masses, and then discuss how these pseudocritical temperatures extrapolate to the unique chiral phase transition temperature in the chiral limit at vanishing values of the chemical potentials. So as I said, one looks, for instance, first at the order parameter of QCD. I introduced here a particular version which eliminates not only ultraviolet divergences, but also eliminates the leading linear parts of the regular terms, and that makes the determination of a critical point easier at finite values of the quark masses, as you will see in the following. So one calculates the order parameter as a function of temperature for various values of the quark masses. One sees the temperature dependence and the characteristic quark mass dependence, and eventually when one extrapolates to the chiral limit, one ends up with this black curve for the order parameter, and the point where the order parameter vanishes, that is the critical temperature in the chiral limit. The scaling properties of the order parameter allow us to rescale this result coming from various values of the quark masses or symmetry breaking fields in terms of a unique function, as you can see in the right-hand figure, and that tells you that one has indeed good scaling properties of the various observables at also already at finite values of the quark masses. So one then can take derivatives of the order parameter either with respect to quark masses or with respect to temperature. One can locate the peaks in these susceptibilities which define a pseudocritical temperature. And as you can see, when one starts with a rather large quark mass, ml over, so light quark mass divided by strange quark mass, like 1/20, 1/27 corresponds to the situation of physical light and strange quark masses. So as one starts with a large light quark mass and decreases it with time, then one sees that the susceptibilities all develop a huge peak, which eventually signals the appearance of a phase transition in the chiral limit. And this peak position shifts to smaller temperatures as one reduces the quark masses. And you see that when I introduce various susceptibilities to define a pseudocritical temperature, I usually get peaks at somewhat different values. Yeah, sorry, the question? No question?
Frithjof, actually, I had a question a couple of slides ago.
Yeah.
Slide 14, maybe.
Sorry?
Slide 14.
Slide?
Hello?
Yeah, which slide?
14, 1-4.
That is this one.
Then 12, maybe. Huh? 2 slides ago, where you had the Z2 and the O4 slides.
This one.
Yeah. So the two functions are very similar. So how do you distinguish? I mean, if you find that the data, agree with one of these functions, how do you distinguish between Z2 and O4?
Yeah, so that is correct. They are quite similar in these cases. They are, of course, quite different in terms of the critical exponent alpha. So the Z2 has a positive value of alpha. So when you would calculate a specific heat-like susceptibility, you would see that the Z2 susceptibility diverges, whereas the O4 does not diverge. But in general, when I stick to the magnetic susceptibilities, so what one has to do is one really has to study in detail the divergence of susceptibilities in the chiral limit and extract from the peak heights this factor here which controls the divergence, and then you have to determine the critical exponent delta, for instance. The delta is different for different universality classes, but it's also not Z different. So one really needs a good precision to distinguish, for instance, Z2 from O4, just in terms of magnetic susceptibilities. But the thermal susceptibilities will be quite different in both cases.
And thermal susceptibility is chi T, right?
Yes. In this case, I define the chi T as a mixed susceptibility. So mixed susceptibility is the derivative with respect to quark mass and temperature. So a thermal susceptibility would really two derivatives with respect to temperature. So really a specific heat.
Got it. Yes.
Yeah.
Thank you.
Okay. Okay, so I tried just to say that one has various ways of extracting pseudocritical temperatures, and these three ways I showed here on the previous slide. I just used the peak positions of these three different susceptibilities to define the quark mass dependence of pseudocritical temperatures, which you see in this figure. So of course the different susceptibilities give you different pseudocritical temperatures. However, when you extrapolate them to the chiral limit, you get a unique determination of the chiral phase transition temperature. At this point I should say that all these calculations I show you here are done not in the continuum limit, but just for a fixed value of the lattice cutoff, which means in this case the temporal extent of the four-dimensional lattice had only 8 points. So eventually one wants to let this number of points go to infinity to extract the chiral phase transition temperature in the continuum limit. And that actually has been done for yet another set of pseudocritical temperatures, which I introduce in this figure here, in this slide here. So rather than using the peak of the susceptibility as a pseudocritical temperature, one uses susceptibilities at 60% of the peak height, which has the advantage defined susceptibilities or pseudocritical temperatures is particularly weak and allows a quick extrapolation to the chiral limit. And that is shown here in the right-hand figure. So when I calculate as a pseudocritical temperature the value of the susceptibility at 60% of its peak height, it has a very weak quark mass dependence and allows for a rather quick and easy extrapolation to the chiral limit. So the outcome of such studies for QCD is that when one is at vanishing values of the quark masses, then one can extrapolate from the situation of physical light and strange quark masses to the chiral limit, and one finds that by going from physical masses to the chiral limit, the chiral phase transition drops by about 25 MeV, which, as you will see, is a rather big effect for QCD. So now we know the chiral phase transition temperature at vanishing values of the critical potential, the vanishing values of the baryon and strangeness chemical potentials, and I want to show you the results, which are actually our recent results coming from this publication of the last months, which we did with the hot QCD collaboration and which mainly has been performed by Mukto Osaka, who was a postdoc in Bielefeld and now is a postdoc in Japan, in Taiwan. So what we do here is we calculate the dependence of susceptibilities as a function of chemical potentials and follow on the one hand how the pseudocritical temperatures at physical values change with values of these chemical potentials, and on the other hand how this change varies when we go closer and closer to the chiral limit, which eventually gives us a result for the curvature or the dependence of the chiral phase transition temperature on values of the chemical potential. And yeah, as I said in the beginning, we cannot do direct calculations in lattice QCD at non-vanishing values of the chemical potential. So what we do is we use Taylor expansions of various thermodynamic quantities. For instance, the Taylor expansion of the order parameter susceptibility, the magnetic susceptibility around the pseudocritical temperature at vanishing chemical potential. We expand that in a Taylor series by taking temperature and chemical potential derivatives and also higher orders. And then we demand again that the susceptibility has a peak, so there should be a point where the temperature derivative of the susceptibility vanishes, and that defines the so-called curvature coefficient kappa 2, which gives you the variation of the peak positions in the susceptibilities, and as such the variation of the pseudocritical temperatures as a function of various chemical potentials. So that has been done some time ago already for values of quark masses that correspond to the pseudocritical temperature, and we know that starting at the pseudocritical temperature, varying the baryon chemical potentials and calculating the shift in the pseudocritical temperature, the variation of the pseudocritical temperatures is rather weak, characterized by a small value of the curvature coefficient kappa, and the next correction to that, the kappa 4, at present is actually found to be 0 within errors. So what I want to do is extend this calculation to smaller values of the quark masses and then extract the corresponding curvature coefficients for smaller values of the quark masses so that we arrive at the chiral limit eventually. In that case, the situation is a little bit easier because we again can make use of scaling properties of the QCD free energy in the vicinity of the chiral transition, and using the dependence of the singular part of the free energy or the pressure as a function of temperature and quark mass like variables, we can express the temperature like variable again as a series in terms of temperature and chemical potentials, because the chemical potentials do not break the symmetries of QCD. And as we eventually at the phase transition point need that the scaling field T has to vanish, we can use derivatives of the order parameter with respect to chemical potentials and temperatures respectively, and find the condition that is needed to make the reduced temperature variable vanish. So that allows us to define the curvature coefficient in terms of a somewhat simpler quantity, namely just second order derivatives of the order parameter with respect to baryon chemical potential and with respect to temperature. And one can go on and generalize this not only to baryon chemical potentials, but also to strangeness chemical potentials. So when I look at the dependence of the temperature-like variable in the scaling fields, then it depends on baryon chemical potentials, strangeness chemical potentials, and certain mixed terms. All of them come with an expansion coefficient that can be calculated similarly to what I said here for the curvature coefficient in baryon chemical potential direction, so that I can do also for strangeness direction and for these mixed directions. And that allows me then to define the variation of the pseudocritical temperatures with various chemical potentials. And yeah, so here's a calculation of these various ratios of order parameter derivatives with respect to baryon strangeness and mixed chemical potential combinations and the temperature. And we want to extract these ratios at the chiral phase transition temperature or at the pseudocritical temperature at a certain value of the quark mass. And that allows us to define the various curvature coefficients kappa 2b, kappa 2s, and kappa 11bs in terms of corresponding curvature coefficients in the flavor basis, which I discussed not here, but in principle one can always use baryon chemical potentials or flavor chemical potentials in equivalent fashions. What one learns here, for instance, is that the curvature coefficient in strangeness direction, which you see here, is about an order of magnitude, strangeness flavor chemical potential is about an order of magnitude smaller than the curvature in the light quark or light chemical potential direction. However, when you go to the baryon and strangeness basis, then the curvature coefficients in both directions are quite similar. So that allows you to define the surface of critical temperatures in the baryon and strangeness chemical potential planes, and I already show here the surface for the in the limit of vanishing chiral chemical potential, vanishing light quark masses, where one extrapolated results at different values of the quark masses to the chiral limit. And on this surface I have drawn various lines. Some of them are of theoretical interest, like the lines where one sets the strange quark chemical potential to zero, or the line where one sets the strangeness chemical potential to zero. And one of the lines is of particular interest for the study of the chiral phase transition in heavy ion collisions, which corresponds to the situation where actually strangeness is set to zero. And because in a heavy ion collision in the experiment, the incident nuclei don't have strangeness, and strangeness stays conserved, so net strangeness stays zero in heavy ion collisions. That leads to a particular relation between baryon and strangeness chemical potentials, which is indicated by this black line. And it is this black line on which heavy ion experiments study the QCD transition from the low to high temperature phase. And what we learned from the study I've shown here is that the curvature coefficient along this black line is about 10% smaller than the curvature along vanishing strangeness chemical potential, which means it is about 0.014 or 13. Okay, so this is actually the outcome of our new calculations, that we now have a result on the curvature of the chiral phase transition line at vanishing quark masses, vanishing light quark masses, and we know how the chiral phase transition temperature changes with baryon chemical potentials. And that brings me to my conclusions, where I try to make use of these results and relate them or extract some relevant statements for searches for the critical QCD critical endpoint in heavy ion collisions. So what we learned from lattice calculations is that the pseudo-critical temperature at physical values of the quark masses and vanishing chemical potential drops by about 25 MeV when we go to the chiral limit. And then this chiral limit result for the transition temperature keeps dropping when we switch on baryon and strangeness chemical potentials. And the drop is sort of given by this term here, which I give. So it drops by about 2 MeV when the baryon chemical potential over temperature is about 1. Which doesn't sound much to you, but it's in some sense quite substantial. So first of all, what we can extract from our knowledge of the chiral phase transition temperature at vanishing chemical potential is a rigorous bound on the possible temperature at which a critical endpoint can be found in QCD. So it is certainly smaller than something like 135 MeV, because the critical endpoint temperature needs to be smaller than the chiral phase transition temperature at vanishing chemical potential. But then we also know that from various calculations, which I cannot discuss here, that the tricritical point is most likely larger than, at a chemical value of the chemical potential, which is larger than mu b over T being 2. Most values actually find in model calculations that it is larger than 3 or even 4. So being conservative and saying that the tricritical temperature is to be found at a value of mu b over T being larger than 2, we already conclude that the critical endpoint temperature has to be, or is most likely, smaller than 125 MeV. So larger values of mu b actually put it close to 100 MeV. But I think estimating it to be smaller than 125 MeV is sort of a conservative estimate for it. And this has some drastic or relevant effects for searches of a critical endpoint in heavy ion experiments. So when I say that mu b over T is to be larger than there's a square missed. Sorry. Okay, so for some reason I gave here this estimate for mu b over T being of the order of 4, which is one of the actually more stringent estimates than this value of mu b over T being 2. But anyhow, so if we say that mu b over T is of the order of 4 as various, no, sorry, I screwed up that statement a bit. So what I said is the critical endpoint temperature has to be smaller than 125 MeV. And when I look at my relation for the variation of the transition temperature as function of the baryon chemical potentials, then I conclude that in order to reach a temperature that is smaller than 125 MeV, I actually need not only a mu b over T larger than 2, I need a mu b over T that is about 4. So when mu b over T is about 4, then the transition temperature turns out to be about 125 MeV. And mu b over T means the baryon chemical potential needs to be large. It needs to be of the order of 500 MeV. And the consequences of a baryon chemical potential of the order of 500 MeV that one can extract from various studies of heavy ion experiments, which determine the temperature at the time where quarks hadronize and come back into a hadronic phase. And they find that as one varies the beam energy in the heavy ion experiment from large values to smaller and smaller values, the baryon chemical potentials of course increase from almost 0 at collider energies of about several hundred or several GeVs down to beam collider energies of a few GeV, where one finds baryon chemical potentials which are of the order 2 or 3 times the temperature. What one concludes is, in order to get into a region where baryon chemical potentials are of the order of 4 times the temperature, the beam energies need to be small. They need to be actually of the order of 5 GeV, square root of S. And that is of relevance for the design of heavy ion experiments. Actually, it turns out that all the collider experiments which at present searched for the possible existence of a critical point are done at beam energies which are too large to possibly find a critical endpoint. So the current beam energy scan at RIC, for instance, goes down to beam energies of about 7 or 8 GeV, and a small value like 5 GeV at GSI. So that is telling you that if one hopes for finding a critical endpoint, one still has to wait for the next generation of heavy ion experiments. Okay, I guess with this I want to stop and conclude my talk. Thank you for listening, and if you have questions, I wait for that.
Thank you, Frithjof. Thank you for the very nice talk. Do we have any questions from the audience?
Hi, I would like to ask sort of a question about what kind of. I know that most of the work you presented today is about finite temperature phase transitions, but what can you sort of educate us about what is known about the structure of the phase diagram at low temperatures, and whether there are any quantum phase transitions that one expects in QCD? When you have 2 or 3 flavors of quarks.
Yeah, so this, when you talk about quantum phase transitions, I think then the relevant lattice studies on that is the discussion of QCD with many number of flavors. And one usually says that the conformal, in the conformal limit of QCD, the critical temperature goes to 0 at a certain number of flavors.
Okay.
And that is sort of the quantum phase transition you are thinking of. So that with QCD, with very many number of flavors, which means of the order of 10 or probably 12, one ends up with a phase transition at 0 temperature, which then is a quantum phase transition.
But we don't know much about what happens for do we know anything about what happens for the real world QCD, which is like with 2 or 3 flavors at very low temperatures?
Well, that is, I think, in this phase diagram. I mean, certainly, of course, you don't know anything from lattice calculations, but there's this discussion of going into a color superconducting phase with pairing of quarks.
Right. Okay.
That is a completely different regime, and that may have some relevance for physics in the core of dense stars.
Right.
Yeah.
Okay.
But yeah, so that is discussed in let's say, first of all, in perturbative calculations at very high density and zero temperature or small temperature, and then also in various model calculations.
I see. Okay, thank you.
Yeah.
We also have a liquid gas light phase transition somewhere, right?
Yeah, so the liquid gas, oh, sorry. There is not in this phase diagram which I used here for illustration, but there is, of course, the liquid gas transition somewhere at or below nuclear matter density, which is a phase transition from vacuum to nuclear matter. That is a first order phase transition. And this first order phase transition extends a little bit into the finite temperature region and also ends up at a second order endpoint. And that is, as Prasad says, the liquid gas transition.
I see. Okay. Yeah, thank you.
Do we have any other questions? Maybe I can. I missed the distinction between N.
Yeah, that is because I sort of skipped my discussion of the change of basis for the chemical potentials. So we can discuss, I mean, the natural way to discuss density dependence in QCD would be to introduce chemical potential for different quark flavors, which is the light quark chemical potential and the strange quark chemical. In contact to, let's say, the heavy ion community and more phenomenological approaches, we usually go into the conserved charge basis of baryon number and strangeness. Baryon number, strangeness, and also electric charge. And these two sets of chemical potentials, they are simply related to each other. So you can either talk about flavor chemical potentials or conserved charge chemical potentials. Baryon and strangeness number, or flavor number, light flavor number and strange flavor number.
Okay.
And in theory, on the lattice, it is, for instance, convenient to set the light quark chemical potential equal to the strange quark chemical potential. That means one is effectively dealing with a particular combination of baryon and strangeness chemical potential. And that is sort of indicated here in this surface. When I set the strange flavor chemical potential to 0, then I'm effectively discussing a line in this plane which corresponds to certain non-vanishing baryon and strangeness chemical potentials.
Okay.
That is sort of is of relevance when you compare results on curvatures coming from different groups. Some to 0, others set the net strangeness number to 0, and others set mu s to 0. So, and as I indicate with these numbers here, the results differ then by some 10 or 15%.
Yes. Yes, yes. Yeah. Thank you. I missed that. Yes. Do we have any other
Frithjof?
questions?
I have actually a question. So, how do you actually conclude that your baryochemical potential for tri-critical point will be greater than 2? Would you kindly repeat that point? I mean,
Yeah, I cannot repeat it because I did not really say it. But
yes, that's fine.
yeah, right. So first of all, there are studies of other thermodynamic quantities in the Taylor series, which are done to, at present, up to 8th order in the Taylor series. And then one can use standard criteria to discuss the radius of convergence of this series. And the radius of convergence provides an estimate for a possible critical point at real values of the chemical potentials. And these estimates for the radius of convergence are currently always in the region mu over t larger than 3 or around 3. That comes from studies of the Taylor series, but that also comes from numerical simulations at imaginary values of the chemical potential, where one actually can find poles of the partition function in the complex plane. So all these various studies suggest that on the real axis there is no singularity at mu b values smaller than 3 times the temperature. And that let me say it is sort of likely to be larger than 2.
Okay. And this is of course in the chiral limit, right? But like
Yeah, right. Yeah.
Yeah.
Actually, Sabinya's question also reminded me, Frithjof. You didn't discuss much about the Pade approximants or the poles or zeros of the partition function. So I mean, that's like a separate approach to the same thing, or?
Well, the Pade starts with using the Taylor expansion approach, and then, as usual in statistical physics, you have a series for a certain thermodynamic quantity, and you approximate this series by a Pade approximant. So in that sense, Pade is nothing else but a resummation of the series that you know. And then the poles of the Pade are used to estimate also the radius of convergence or the critical points. So Pades give results that are consistent with simple ratio estimates from the Taylor series.
Okay.
And nowadays these multi-point Pades are very popular to study results coming from imaginary chemical potentials. So that is a new way of looking at locations of Lie-Yang zeros in the complex plane, which allow you to extract information on the location of the critical point.
Yes. Thank
And
you.
Frithjof, I have one more question. So
Yes.
I mean, as mentioned in this slide, that the chiral temperature, I mean, in the chiral limit, the TC becomes 132 MeV more or less. But I think there was also one plot in which you showed that the chiral temperature is around 143 MeV, right? Is it?
Yeah, that was my warning that these figures.
Yes, I think.
Yeah,
Yes,
these-
this one. Yes.
These figures are all shown for a fixed value of the
N tau.
cutoff, n tau equal 8.
Okay.
And so eventually you have to do these calculations for larger values of n tau, which is done for in practice for n tau equal 8, 12, and 16, and then results are extrapolated to the continuum limit. So that is these kind of extrapolations that you see here.
Yes, yes. Thank you. Thank you.
Yeah.
Okay, do we have any more questions? If not, thanks. Let's all thank Frithjof for a very nice talk. It was really very interesting, and especially this very recent work, which was, which is very new, but seems to, have a lot of relevance for what to do next as regards this search for the critical point, which has been going on now for quite some time. And,
Yeah, yeah.
it should be interesting. It should be interesting.
Okay, yes, thank you for inviting me, and sorry that I screwed it up the last time, and I hope.
This talk,
No,
yeah,
it's
this
okay.
talk, I think, made up for everything. So
Yes.
thank you very much.
Thanks,
you so very
thanks
much.
for listening. Yeah, goodbye. Bye-bye.
Bye-bye.
Bye. Bye.